planning at the team. I took the tapping at my class in. So definitely can you believe me that I know a team? Father begins. Yes, yes. Yeah. Susan.
So far we have calculated all the source site and path and all the response, and also we have calculated the spectral acceleration, peak ground acceleration, spectral velocity, peak ground velocity, peak ground displacement. So these are the things we have computed from the record, and then we try to estimate what will be the seismic hazard at a particular regions, and how to incorporate this observation for a particular site into that hazard analysis. So these are the things we have to consider today, and so it will not be finished today definitely, because it is a little bit extended chapter. It will take another day also to finish it, but let us start from the beginning. And I hope everybody has done the statistical analysis, right? So in your course you have done the statistical things, so you know how to calculate the random variable and the probability and the cumulative probability and all these things, right? Looks to be familiar, right? Yeah. So that is what we will be using it, and we will be using few types of distribution function that includes the normal distribution as well as the Poissonian distributions. Because earthquake occurrence, we will be model it as a Poissonian distribution, right? So you know where the Poissonian distribution can be applied?
Accidental events. Using them. Yeah, for a particular time interval of this, like the number of accidents or the number of something that's right. So if something has happened over an interval of time or over an interval of space, then how many times it might occur? So that is your exceedance. If that has to be modeled, then the Poissonian distribution we will be applied. Okay, because that's a Poissonian distribution case. Say suppose if you are standing in a road, say suppose from Eisen Gate to the to the railway station, in that stretch of the road, we say that okay, on an average, there are 2 or 3 accidents
per month. Okay, so I need to calculate what is the probability that it will have a 10 accident in a year. So if that type of things is required, then we will be calculating based on that. We will be applying the Poissonian distribution if I know on an average how many accidents took place. So if I know that, then we can calculate that part. Okay, so that is one part which we will be using, and the next part is all our science and the engineering things. We all assume that the distributions are always follow a normal distribution or the Gaussian distribution. Then that distribution we also need to apply. So this is a probability calculation is on that aspect, and we will be develop that relations. Okay. Now, so let's see. So this is your, we have all understood that where do the earthquake occurs. This is the very first slide I had shown it. And so the where do earthquake occurs, we all see that this earthquake occurs along the plate margin, and also it is occur on the fault in a particular intercontinental part, right? And the occurrence is also the number of occurrence, and the number of earthquakes in a particular area is also varies. So therefore we need to develop some, whenever you are trying to assess for the earthquake hazard, we need to keep these things in mind, that the earthquakes occurrence are not same in everywhere. So that is why we have to do the probability part. And you all know by these things that the earthquake size, with all the scientific aspect, that this is all depends on the seismic moment, and the seismic moment is basically related to the seismic or the MW magnitude, or the moment magnitude scale. So this is m0 equals to mu a d bar. So d bar is the average displacement, and MW equals to 2/3 log 10 m0 minus 6.03. So that's your seismic moment part. Okay. So this is what we have done, and we are interested that a particular site, if it is located, then this particular site is very near to the various earthquake source, and this source we are defining some source as a line source, some source as a area source. So that means we try to calculate how much or how many earthquakes can come over this area, or sometimes we will calculate how many earthquakes are basically rupture, or what is the length of the rupture, or where the length of the rupture along this fault. So which is a linear things, right? So there are we need to define the geometry and also the area of the sources, right? Now, so the first of all, again, we come back to the earthquake size. There is a fundamental difference between the approach of the seismologist and approach of an engineer, right? So seismologist uses the small magnitude and try to calculate the source characteristics and crustal structure based on the small magnitude earthquake, whatever they had, and try to be satisfied on that. But the engineers are interested always in the big magnitude. Engineers are not interested for a small magnitude earthquake, because they can, that small magnitude earthquake is not creating any damage or any hazard to the structures or anything, right? So they are not interested to measure the small magnitude earthquake. So they are always interested to measure the big magnitude earthquakes, and its consequences they need to study. Now, in order to do so, they are basically try to interested in a minimum magnitude for that area, or an area which can produce, and also it can go from the maximum value a fault can produce, right? So a minimum to a maximum, that is what they are interested to understand, and that is where they were trying to do the hazard based on that. Okay, so so basically a particular fault or particular rupture of an area of a fault and the magnitude, amount of magnitude it releases, these are the important things to study. So what is the area of rupture it could happen on a fault, and if that is the rupture, then how much is the, how much will be the magnitude, right? So for any magnitude and area relation, they need to establish. So that means they need to have a in mathematics term, we call it as a conditional probability. So that means we when I call it is a conditional probability density function. So we call it as a conditional probability density function. So density function is the basically PDF, the probability density function, and conditional means that, so this is the condition things, right? So this is the condition A has occurred, then what will be the magnitude it will release. So that means it is a, if the area A has been ruptured, then the probability of what will be the magnitude will be the M. So that mathematically we show it as a M vertical bar with a, right? It's a conditional probability. So so that will be developed from the, that is what we like to develop from the empirical data, right? Okay, now let's see. This minimum magnitude, whatever we were thinking that we earthquake engineers are interested in, that may vary, right? Say suppose in California, in US we were using the magnitude 5 as a minimum magnitude because engineers are not interested if the magnitude is less than 5, right? Because that magnitude, they believe that all the buildings and the houses and the bridges they had constructed, they can easily sustain with a 5 magnitude earthquake. Even if it is a shallow, it will be fine. So 5 magnitude earthquake, they take it as a minimum, and then at a particular area, whatever is the maximum took place, that's a fine. That they can use as a maximum magnitude, or we call it as a M max. So M mean and M max, these are the things. But in Europe, where the buildings are old and mostly the brick structures, they uses the minimum magnitude something around 4 to 4.7 depending upon the places, right? So and some of the anthropogenic zones where there is some of the human activities are there, then they call the minimum magnitude, it is a 4.5 to 5. So this 4.5 to 5 is the choice of the engineers for the minimum magnitude definition, and the maximum magnitude, whatever it can occur, that we all needs to address. Okay, so so therefore the average amount of or the average stress which is released by the fault is basically related with the magnitude of that place or on the fault, right? So we that has been studied, right? So that means what will be the length and width of the fault if it's ruptured, then what will be the amount of magnitude it's generated. So this also has been studied for the number of earthquakes all over the world, and there is famous relation. It is called Wells and Coppersmith relation of 1994. They had studied the lot of the earthquakes, its length and the width and the magnitude amount of release, and calculated some of the regression analysis and come out with a relation that m equals to a log 10a plus a2. So this a1 and a2 are the two constants, right? And these constants are given here. So this is 0.98 to 4.07 a1 and a2. So this is for overall things, and the sigma or the standard deviation of magnitude plus or minus, this will be equals to 0.24, right? So you can calculate this one and then plus 0.24 or minus 0.24, plus minus 0.24. So if it is a strike slip fault, then this will be the main part. If it is a reverse fault, then this will be the magnitude. So depending upon because they had done extensively on the, as I told you, that all our data are heavily weighted with the California data. So although they had collected all over the world data, but the California is still getting a little bit weightage. Okay, so if we know the length and width, then of course it is a shallow focus earthquake. All the earthquakes they had used are basically the shallow focus and also in the active tectonic zones. Okay, so these are some of the conditions that they had used it for the active tectonic areas, and also it is a shallow focus one. So then that magnitude we can calculate. So that is what I am try to tell m and a particular relation that we can establish. Okay. Now similarly, we can also calculate how much will be the moment release by the earthquake in that, or the seismic moment from that area of rupture. So this is your A3 and A4, and this is also this A3 value for active crustal region, deep slip part, active crustal region for the strike slip, and stable continental regions. These are all given, and if you can, so that is your seismic moment value, and if you see this graphical part, you can find out that if this is your area of rupture, if you can calculate the area of rupture, and then you can just directly calculate the seismic moment based on this particular relations, right? So that you can calculate, and on the left hand side they have a seismic moment magnitude MW. So you can put this line on this side, then you can calculate the seismic moment. So for a given area, just you calculate this one and find out this will be the seismic moment release, and this will be this seismic moment, right? So that's the Newton meter calculations. Okay. Any question up to this much?
Long back, it is not for the earthquake hazard. It is not for the earthquake hazard distribution. The Gutenberg and Richter, they had observed that this
long back, it is not for the earthquake hazard. It is not for the earthquake hazard estimation. The Gutenberg and Richter, they had observed that the small magnitudes are occurring lot of, in number there are a lot, but the big magnitudes are occurring very few. Okay, so they thought that there is a relation with a number of earthquake happening with a small magnitude and the earthquake happening for a big magnitude, and they had not done anything at that time. The earthquake hazard has not been done at all, so they plot a relation with a number of earthquake and the magnitude. Okay, and that relation is called Gutenberg and Richter relation. So that relation shows that as the magnitude increases, this will be there is a decay like this. So that means this is a number of magnitude earthquake occurs. So basically, big magnitude earthquake are occurring very less in number, but if it is a small magnitude earthquake, it will be large, right? So this is what we call it as a Gutenberg-Richter scale, or Gutenberg-Richter the relation, right? So this relation was, although this is your n number of earthquake, but that has been modified by the earthquake hazard analysis group. So they call it as a, so instead of a n, we are writing as a lambda. So lambda is the basically it is a number of earthquake having a magnitude greater than a particular magnitude, right? So this lambda means the magnitude to be greater than a particular magnitude, and that will be equals to a to minus bm, right? So that according to the Gutenberg-Richter, this is a log n equals to your a minus bm, right? So that they are saying that log n let's be replaced with your activity of the fault, right? So that will be equals to this one. So this 10 to the power a, okay, so 10 to the power a is basically the activity rate of that particular zones, and and this is your total number of earthquake per year having magnitude m greater than 0. So that is your number of earthquake m greater than 0. So that is what we call it is a 10 to the power a, right? And b is a parameter which is called Gutenberg-Richter parameter. We call it as a b value, and this b value is basically related to the slope of this curve, right? So some point it might be slope like this, some area the slope might be like this. So how much will be the slope between the n and m of a particular fault part or particular zone? That is what we are trying to calculate. Now, if your m equals to 0, that means m, this will be a 0 magnitude. So whatever is the number, that will come to the 10 to the power a. So you can calculate the value of a on that part, right? Now, this Gutenberg-Richter scale is a unbounded scale, right? So that means it will be going from the 0 magnitude to any big magnitude it is possible. So then you plot it, and then that scale you can calculate, or that line you can draw. But as our earthquake and as the engineering approach to the earthquake, it is a bounded part, right? So that means we cannot see the entire earthquake of 0 magnitude, and we cannot have maybe, say suppose if a particular fault has a maximum magnitude is 6.5, so we are only limited from 5 to 6.5. So that is why our relation is a bounded relation. So the Gutenberg relation is an open money relation from the zero magnitude to any magnitude possible. But if it is a bounded magnitude, then we call it as a bounded Gutenberg-Richter relation, right? So, so based on that, we have to calculate the activity rate of that fault. Okay. Now, so we are trying to do these things with this idea. Now we express this money relation as a exponential part. So basically alpha is equals to therefore 2.303 of A and beta equals to 2.303 of B. So that is a conversion from the log base 10 to log base E type of things. So lambda m is equals to 10 to the power, if you can see it here, so lambda equals to 10 to the power A by A minus Bm. So then if you can do that, we can write it as a exp of alpha and beta m. So that means 2.303A and B equals to 2.303B, right? It's clear to everybody, right? Huh? So log 10 to log E conversion. Okay. So what is the condition here is the probability. So probability of the magnitude to exceed a particular value m, right? So the magnitude m is the capital M is the magnitude, any magnitude to be exceed a particular value m, provided or with the condition that m is greater than 0, right? With the condition, so that is the conditional probability, is equals to lambda m by lambda 0, right? So exceeding with a lambda 0 by lambda m. So the lambda m equals to e to the power exp alpha by bm, and this will be equals to, this will be equals to lambda 0, right? So that is equals to lambda 0. So if you can put this lambda 0 means exp of alpha, so then it will be e to the power minus bm, right? So this is your exceedance, right? So that means it exceeds a particular value m. Now, if it is a cumulative probability, so what is the cumulative probability?
Probabilities you need to add up to that probability. So that is your cumulative probability, right? So cumulative probability means that the magnitude to be less than magnitude m, right?
It is you need to add up to that probability. So that is your cumulative probability, right? So cumulative probability means that the magnitude to be less than magnitude m, right? So basically what we write it in statistics, the cumulative probability fx is basically the probability of any random variable x to be less than equals to x, right? So that's your cumulative probability. So that means if you have a probability, say suppose this probability is like this, then this probability is like this probability is like this, say suppose this is your probability for x equals to 1, this is the probability of x equals to 2, this is the probability of x equals to 3, and these are all the probability values. Okay, so these are the probability values for the P1, P2, P3. So if you do all the values till the 3, then it will be always less than or equals to 3. So that's the definition of cumulative probability. So this is probability of m less than equals to m. Please remember this is a less than equals to m. So that will be equals to cumulative values. So that is your fm, this one. So that means since it's a greater than m is lambda m by lambda 0. So therefore, less than m will be equals to 1 minus this one, right? So basically the probability of x less than equals to x this. So f greater than equals to x means it is a 1 minus of fx, right? So that is the rule. So therefore cumulative distribution function is equals to 1 by this one. So this is 1 minus beta m, right? So that is your probability of m, and that is your cumulative probability. So we will be remembering this one. So this is the cumulative probability is equals to this much, right? Now, if I know the cumulative probability, then I can calculate the probability density functions, right? So this probability of x less than equals to x, that means we are trying to do all the integration up to the x, right? So that means we are trying to calculate the probability of x. This is your dx. So we are doing the integral, right? So integral means we are trying to calculate all the values and add them together, right? So if that is your fx and this is your px. Now if I need to calculate px, so then we have to do a differentiation of your fx, right? So then it's a differentiation of fx. So therefore fm, so if it is called a probability density function, so PDF function, this I call it as a small fm. So that means it is your ddm of, this is your cumulative probability, right? So that means if you have a cumulative probability of this one, then if you can do that differentiation, it will be beta into e to the power minus beta m. So these are the two things. One is the fm will be equals to 1 minus e to the power minus bm, and the fm is equals to f equals to basically beta into e to the power minus beta m, right? So that's the two things, cumulative and the probability. Okay. So that's the definition of the things, and as I said that we are truncating it, right? So basically we are doing it from m min to m max. So that zone we are trying to do. So we are trying to calculate what is the probability that if the fault ruptures, then that rupture will be between m min and m max, right? So that is what we were trying to calculate, right? So this is what we call it a truncated probability. So our objective is to calculate cumulative probability fm, cumulative probability fm of magnitude m, right? But this magnitude should be between m min to m max. So this magnitude lies between m min to m max. So we are trying to calculate what is the cumulative probability when with the condition that the magnitude will be between m min to m max, right? So that is what we were trying to calculate. So that means it is so this is your cumulative probability. So as I said to here, the cumulative probability means it is m less than m, right? So cumulative probability means probability with a m less than m. So therefore this is the probability of m less than m. So that's the case because that is your fm, and that will be conditioned with m min and m max, and that will be equals to, if you can do that, that will be, so we, instead of a m, we write it as a that beta 1 minus beta e to the power m minus m min and m max minus m min. So m minus m min and m max minus m min, so that we need to calculate, right? So that's your FMM. So if you know this FMM, then you can calculate what is the, so this is your cumulative density function and this is your probability density function. So PDF will be just, so PDF will be equals to DDM of CDF. So therefore just differentiate this expression. So FMM will be equals to FM M minimum to M maximum. So then I differentiate this expression. So this expression, if I differentiate it, then it's a beta into e to the power minus beta m minus m, and then beta into this one, right? So that's your truncated probability. If it is between m min and m max, then it will be like this. Okay?
Highest kind
Magnitude.
like recently we had 8.6. So it is like our capability of pressure rate is at full, I think, in Bible.
Yeah.
Like in day. In that week said when years of become of experience. In exceedance, maximum.
Exceedance of the minimum magnitude, that means the threshold, and it could go up to M max. Right? So M max we don't know. And okay, but we know some way that we know that the particular fault can have a generation based on the these things, that they can have a potential of generating this much magnitude of earthquake. So depending upon their extinct rate and all on these things, we have some idea. And geologists have some idea that this might be potential.
So depending upon their slip rate and all these things, we have some idea. Geologists have some idea that this might be potential. This fault might have a potential to generate 8 magnitude earthquake, or might be the 7 magnitude earthquake. So that will be considered as a M max. So yeah, but whether truly it will generate always that things or not, it's anybody's guess. But that's the maximum magnitude. So we exceed the minimum threshold. Okay. So that's your exceedance. So M min, M and M max. So this you can differentiate this expression. So from there you can calculate this value. Okay.
No, or the range is from the 22 to 6. And there's some people that is within 4.4, 400. How do we understand that the next week will be like will it focusing so it can also greater than 6?
No, the greater than 6, there is a possibility, right? Because that is your Wells coupled with money relation. If you know the money area of the fault, and if you know the length of the fault, length and width of the fault, you can calculate area, and from that area, you can calculate the potential.
Right, because that is your Wells coupled with money relation. If you know the money area of the fault, and if you know the length of the fault, length and width of the fault, you can calculate area, and from that area, you can calculate the potential of the magnitude M, right? So that you know some rough estimate that it can go up to this much. So that much is very important. But we will be truncate the magnitude minimum level as a 5 magnitude. So 5 is the minimum one. In this any situation, we use the 5 as a minimum, and maximum could be defined by the area of the fault and all these things, and how much slip it will generate. Okay, so basically, So this is your 5 magnitude earthquake. So we will be knowing that this will be the 5 magnitude earthquake, your FMM. So this will be this much. And we have a maximum magnitude, say 7. So the 7 has this many number of maximum earthquakes. So this is your line. So that is your truncated exponential line, right? And we can calculate that from the middle values of these. So this is your delta my, and this is your plus delta my and minus delta my. So to calculate this one, okay? Or if it is a 7.5, we can go up to this much. If it is a 7.5 value, so that's the part. So this slope is equals to the b, and we can see that b equals to 0.8, right? So 0.86. Okay, so we will be writing this one, that FMM will be equals to beta exponential into beta into m minus m mean. If we like to do this one, m minus m mean minus m minus m mean with the 1 minus beta, and that we can calculate here. Okay, so that we can calculate for m mean to m max. So this will be the relation between the minimum magnitude to the maximum magnitude. But if m is a greater than m max or m is a greater than m mean, then this probability is 0, right? So outside that, it is all 0. Make sense? So this is, I have already explained that FMM equals to beta this one, so m mean is calculated. So the activity rate, you can see lambda. So lambda equals to m greater than m mean. So what is the probability that a magnitude is greater than m minimum will be equals to 10 to the power a, right? So from that relation, you calculate from this relation, this will be equals to your activity rate from m equals to 0, right?
This rule here, that for any magnitude, you can calculate this is your delta m, and this is the maximum one on that first, and this is the minimum, or the m mean is the 5. And so this thing that you can calculate here, if you have this much of money, if value is given, we can calculate it from that by using a delta m hat. Right? So it is, we'll show you how to calculate this one. We'll show you in a letter. M mean and M max, and how to calculate that. So outside this, so that means this will be on this side, it is in 0. On this side, it will be also chill, right? So that's 0 values. And the M max is the magnitude physically possible, and that will be equals to 10 to the power a. So, and the cumulative probability, so this will be equals to m mean to the m max. Then it is a 0 for m less than n mean, and it will be equals to 1 if it is a m is greater than m max, right? Because the cumulative probability is 1 if you integrate it. Say suppose in the pictures is like this, is the
right? Because the cumulative probability is 1 if you integrate it. Say suppose if the pictures is like this, say suppose any distribution is like this, right? So here x equals to a and x equals to b, and the distribution is like this, right? So now the question is that what will be the value at this point? So that means this is from here to here, this area has to be 1. Right? Because if it is a b minus a, then this height will be 1 by b minus a. Right? So the area will be equals to 1. So after you reach from the b, then this will be 1. And then if you are going beyond this one, so there is nothing will be added, so it will be still remains 1. Right? So m greater than m max, it will be 1. But m less than m min, so that means this side, these are all 0. So after that, it all increases, and then at this point, this return maximum, and then that value, with that, if you add 0, it will be still be that number. Okay, so this is your cumulative distribution function for different magnitude, and this is your probability density function of this magnitudes. Is it clear? So, if you are doing this exceedance, so log n, or sorry, this we can call it as a log lambda. Okay, so this is the log lambda m to the power m equals to a minus bm. So lambda m greater than equals to m will be equals to the lambda greater than equals to m mean, and then 1 minus fmm of m. So this is your bounded Gutenberg-Richter scale. So bounded Gutenberg-Richter scale is equals to lambda for any value m to be greater than a particular value is equals to lambda whatever will be the minimum threshold, and then 1 minus fm of m. Right? So that is your Gutenberg-Richter scale, and this is equals to your 1 minus fmm is equals to the probability of exceedance. So probability of magnitude of exceedance will be equals to 1 minus fmm of m. Okay. Now, so we need to find out that how many magnitude or how much magnitude will be occurring here, and what will be the frequency of that occurrence, right? How soon that magnitude can occur, and whatever will be the magnitude of that earthquake or that event, right? So for that, we were trying to gather some data. Now this data is from the geodetic measurement, because we are all put throughout the US, we all have a plate boundary observatory, which are basically, we call it as a PBO, which measures that how much a particular zone has been drifted or shifted, right? Say suppose we know in our Alaska regions, the plates are subducting under the North American plate, Pacific plate subducting under the North American plate in a 5.6 centimeter per year. So that is what this plate boundary observatory by measuring the distances, they can calculate, right? So so this is what we always try to calculate, some of the geodetic evidences. Then also we also make some trenches